Density functional theory, DFT. Density functional theory, DFT, is a quantum mechanical theory used to describe the electronic structure of materials. It is a computational method that allows for the calculation of the electronic properties of a system by solving the Schrödinger equation for the electron density, rather than for each individual electron. The basic theory behind density functional theory, DFT, is the Hohenberg-Kohn theorem, which states that the ground state properties of a system can be determined by the electron density alone. The Kohn-Sham orbitals are determined by minimizing the total energy of the system, which includes the kinetic energy of the electrons, the Coulombic repulsion between the electrons, and the potential energy due to the interaction between the electrons and the external potential. The external potential includes the potential from the nuclei of the atoms in the system, as well as any additional potentials, such as those due to an external electric field or solvation effects. The exchange correlation functional is typically split into two parts: the exchange functional, which describes the exchange interaction between the electrons, and the correlation functional, which describes the correlation interaction. However, it can be used to calculate a wide range of properties, including electronic energies, structures, bonding, reactivity, and spectroscopic properties. In density functional theory, DFT, calculations, the basis set is a set of mathematical functions used to describe the electronic wave function of the system being studied. There are two main types of basis sets commonly used in DFT calculations: Gaussian-type basis sets and plane wave basis sets. 1. Gaussian-type basis sets. These are typically used in molecular calculations and are defined by a set of Gaussian functions centered on each atom in the molecule. 2. Plane wave basis sets. These are typically used in periodic solid-state calculations and are defined by a set of plane waves with specific energies and directions. The XC functional is typically divided into two components: the exchange energy and the correlation energy. The exchange energy is the energy gained or lost when electrons are exchanged between two orbitals, while the correlation energy accounts for the many body interactions between electrons in the system. Some common types of XC functionals include: 1. Local density approximation, LDA. This is a type of XC functional that is based on the electron density at a single point in space. 2. Generalized Gradient Approximation, GGA. This is a type of XC functional that takes into account the gradient of the electron density in addition to the electron density itself. 3. Hybrid functionals. These are XC functionals that combine elements of LDA or GGA functionals with exact exchange, which is a more accurate but computationally expensive way to account for electron exchange. 3. Examples of hybrid functionals include BELIP, PBEO, and MO62X. 4. Meta-GGA functionals. These are XC functionals that include a dependence on the Laplacian of the electron density, in addition to the electron density and its gradient. 4. Meta-GGA functionals are more accurate than GGA functionals for some types of systems, but are also more computationally expensive. In general, hybrid functionals are often used for organic compounds and other molecular systems, while GGA or meta-GGA functionals are often used for solid-state systems. The LDA is the simplest form of the XC functional, which is based on the electron density at a single point in space. The LDA assumes that the exchange correlation energy at any given point in space is a function only of the electron density at that point. In other words, the LDA approximates the exchange correlation energy as a local functional of the density, meaning that it doesn't account for any spatial variation of the density. This makes the LDA computationally efficient and easy to implement, but it can lead to inaccurate results for some types of systems. Despite its simplicity, LDA has been successful in predicting a wide range of properties of atoms, molecules, surfaces, and solids. One of the main limitations of LDA is its inability to accurately describe systems with strong electron correlations, such as transition metal complexes and some semiconductors. In these cases, more complex functionals that go beyond the LDA, such as hybrid functionals or meta-GGA functionals, may be necessary to obtain accurate results. Generalized Gradient Approximation, GGA, is a type of exchange correlation, XC, functional used in density functional theory, DFT, calculations. GGA is an improvement over the local density approximation, LDA, as it takes into account the gradient of the electron density in addition to the density itself. GGA functionals describe the XC energy as a functional of both the electron density and its first derivative, the gradient, resulting in a more accurate description of the electronic structure compared to LDA. The gradient-dependent terms in GGA functionals account for the spatial variation of the density and help to capture the effects of electron correlation, resulting in improved accuracy for a wide range of systems. There are many different types of GGA functionals, with varying levels of accuracy and computational efficiency. Examples of popular GGA functionals include PBE, Purdue-Burke-Ernzerhof, BLIP, Beck-Li-Yang-Par, and PW91, Purdue-Wang 1991. GGA functionals have been successful in predicting a wide range of properties of atoms, molecules, surfaces, and solids. However, they are still limited in their ability to describe strongly correlated systems, such as transition metal complexes and some semiconductors. In these cases, more advanced functionals that include higher order derivatives of the electron density, such as meta-GGA or hybrid functionals, may be necessary to obtain accurate results. They are called hybrid because they combine the local density approximation, LDA, or generalized gradient approximation, GGA, exchange correlation functionals with a fraction of non-local Hartree-Fock, HF, exchange. The non-local HF exchange term in hybrid functionals includes contributions from orbitals that are not included in the LDA or GGA exchange correlation functionals. By combining the LDA or GGA exchange correlation functionals with non-local HF exchange, hybrid functionals are able to account for both the static and dynamic electron correlation, leading to more accurate predictions of electronic properties. Hybrid functionals are typically more accurate than GGA or LDA functionals for systems with strong electron correlation, such as transition metal complexes, semiconductors, and molecules with strong charge transfer. Examples of popular hybrid functionals include BLIP, Beck's three-parameter hybrid functional with a Li-Yang-Par correlation functional, PBE0, PBE with 25% HF exchange, and HSE, Haid-Skusiria-Ernzerhof, functionals. One limitation of hybrid functionals is their increased computational cost compared to simpler functionals such as LDA or GGA.